h bar omega. Aha! Okay, so now we're really starting to get results with this second technique, right? We've got the wave function here at the ground at the ground energy, the lowest energy. So we know its form. Now we can find the C by normalizing, as usual. That's quite a complicated business, actually. And we've got the eigenvalue, the ground state, the lowest energy state. It's e to the half. So in terms of big E, it's half h bar omega. So we now got the same results for eigenfunction and eigenvalue. So the wave function and the energy, allowed energy, as in the first case. Right? So this technique is giving us just the same results. Right? So the ground state energy then, we've just derived, e to the half, so therefore it's the actual energy, capital E, is h bar omega over 2. Right? Now we know the energy keeps going down as we step down by applying A minus each time. The energy keeps going down in units, e to minus 1, minus 2, minus 3. So now that we know where the starting energy was a half h bar omega, then we know the whole spectrum. But by spectrum means all possible allowed energy levels. Right? That's the meaning of the word spectrum. All possible energies. Right? So we know all possible energies are of the form a half h bar omega. That's your E naught in a sense. That's your lowest ground state energy. Right? And so if you're going down each time, the energy level goes down by h bar omega. Well, if you go the other way, if you go up from the lowest energy level, you go up, you're adding h bar omega to the energy each time, right? So that's where this comes from. Okay. Now we know the eigenstate, the eigenfunction, the wave function, at lowest level, at lowest energy level. It's of this form, u naught, and we have a formula for it. So now we need to find the eigenfunctions for higher energy levels. So we've got it for u0, but what is it for u1? Like u dashed, if you like. And what is it for u2? Like u double dashed, and so on. So we need a method to find that, and we can still use this technique to do that. Now HW homework. So I'm asking you here to show this is the case, and this time it's a plus a minus u, and before we had a minus a plus u. Okay? So all this analysis here that we did, these few lines here, I'm asking you for homework here to do just the same sort of thing as we did here on the board, right? Do the same, but instead of a minus a plus, you've got a plus a minus, and so you'll get another u dashed, or in this case u double dashed, to distinguish it, and your eta e whatever will change, right? So you'll get this. So this here is equivalent to this, right? So find, where are we? Find this. Calculate. Get this result, and do it for homework. Get this, which is equivalent to this. Right? So just do the instead of doing a minus a plus, reverse it. Do a plus a minus, and you'll get something equivalent to this, which is this, right? And this time your eta here dashed is eta plus 1, whereas before it was minus 1. Okay? And so now we are not stepping down, we're stepping up. Right? So that's why A plus is referred to as the step up operator. Okay? Alright, so effectively then your A plus generates a new eigenstate. Let's call it, let's say we're starting at U0, the ground state, the lowest, the state of lowest possible energy, U0. And if we apply this operator A plus to it, we get a new state, let's call it, well, U1. Right? Now from that, we can do the same thing and get another state, U2, which is thus A plus times U1. Right? So we can generalize. So if you want the nth excited state, excited just means an energy level above the ground state level. So the eigenstate UN, that results from applying this step up operator, A plus, n times to the ground state. Okay? So U2 is A plus U1. Right? Well, yeah, start here. U1 is A plus U0. U2 is A plus U1. So generalizing, UN will just be A plus done n times U0. Okay? So this generating technique here is equivalent to the Hermite, or Hermite if you want to anglicize it, generating function that, you know, we had this from previous session. Right? This allows you to calculate the Hermite polynomials, you know, Hn of z, and you use this, you know, you're differentiating n times blah blah blah. Okay, so this the Hermite polynomial generator, you know, this formula here is equivalent to this. You're just applying the A plus, the step up operator n times, right? So this and this are equivalent. Okay, so we've got all the tools now, this second method, this alternative method, to generate eigenstates and eigenvalues, in other words the wave functions and the allowed energies of the quantum mechanical simple harmonic oscillator. We now have a technique using ladder operators, step up and step down operators, to solve this Schrödinger equation. And this Schrödinger equation is for the simple harmonic oscillator. Right? And I think you know, well, you know, once you've studied it and you've done all the homeworks and you really understand it, I think you will agree with this comment I put down the bottom here, also in the text, elegant, right? Double exclamation mark. Because it's really quite amazing. And this type of technique, for example, you take a state and you apply an operator to it and you annihilate it, like you kill it, you make it, in other words, you make it go to zero. This sort of thing, so-called annihilation operators, and create the equivalent, the opposite equivalent, creation operators. These concepts, these ideas, these tools get used a lot in quantum field theory, QFT, but that's higher level. I won't start talking about quantum field theory until you have a really solid dose of quantum mechanics. So you'll need not only this course at senior level, you'll also need quantum mechanics at M1, first year master's level, and then you know, after those two courses, then we can start doing quantum field theory, QFT, because it's quite a bit harder. But this idea of annihilating operators and creation operators and so forth get used a lot in quantum field theory, QFT. So this general technique of, you know, stepping up and stepping down is gets used a lot in the future. So it's a very handy, very powerful technique, because just by using these stepping up and stepping down operators are able to calculate, to solve this equation, Schrödinger equation, in effect. By solving it, what do you mean? Well, finding the allowed energy levels, quantized mechanics, quantum mechanics, and for the corresponding eigenvalue, what is the corresponding eigenfunction? In other words, what's the wave function? What's its solutions? Well, this technique, an alternative to the more differential equation type M-E to polynomial approach, so this second technique gives you the same thing, the eigenfunctions, eigenvalues. So powerful stuff. I hope you enjoyed it, because it truly is elegant.